first discuss the definition of chemistry. So no matter what level of science that you have undertaken, whether it's just high school or whether you've taken several chemistry courses or science courses for that matter, we all begin in chemistry with sort of splitting things. And the first chemists split matter, which is really anything that has space and has a mass. And they have split matter into the fundamental components of solids, liquids, and gases. But you can do a further split of solids, liquids, and gases and take a look at the molecules and compounds that comprise those solids, liquids, and gases. And then the split can continue further because these molecules and compounds that comprise the three fundamental states of matter are actually themselves composed of elements and atoms. And then finally, you can parse this out into something that's entirely invisible. That is the atom, which is split up into protons and neutrons and electrons. So in terms of detection, we can really detect solids, liquids, and gases. And by that, I mean we can describe a solid by properties. It's hard, or it could be soft, it could be pliable, it could be malleable, it could conduct electricity. In terms of liquids, we can describe them as how viscous they are, in terms of their color, their resistance, or their ability to flow. And gases, we can really describe them in terms of odor, perhaps. We can describe them in terms of mass. But the bottom line is that our senses, whether it's taste, whether it's touch, whether it's eyes, whether it's feelings, excuse me, whether it's odor, we can really describe matter in a macroscopic sense. But then as we go finer and finer into detail, we lose some of that ability for description. Submicroscopic is how I define these finer and finer details of matter, because we really can't see these under a microscope. And then we have the subatomic world, protons, neutrons, and electrons. This is something that has its own math, the math of quantum mechanics, quantum physics. That's how we describe their behavior, the subatomic world. There's a chapter where we just deal with electrons and their capabilities and their behaviors. So these we really cannot describe in terms of behavior, but I can say in the subatomic world we can detect them. So detection is where we really go about talking or describing these two worlds, whereas our five senses is how we describe matter. So then again, as we split everything into finer and finer details, the question comes, what is chemistry? So chemistry really involves a transformation. So whether you're talking about the level of matter at this level, the transformations in going from solids to liquids or liquids to gases, vice versa, or solids to gases, the transformations that undergo or undergone between molecules and compounds, the rearrangements of elements and atoms, the transformations that occur at this level, the release or the abstraction of protons, the release or the abstraction and taking of electrons. All of these transformations, no matter at what level of order or what level of detail you want to describe them, really is chemistry in a nutshell. And of course, chemistry branches out because you have finer subdisciplines in chemistry, like physical chemistry, organic chemistry, and biochemistry. So chemistry, as how I like to define it, is really the study of these transformations, detailing and documenting these transformations that occur at matter, which is sort of at the physical macroscopic world, or the transformations that occur at the submicroscopic and subatomic world. Remember, these we can't really detect. We really can't use our five senses to really understand or grasp. We really look at their detection using instrumentation and whatnot. So chemistry is really detailing transformations of states of matter at any of these levels of detail or magnification. So the question may be asked is, how do we describe these transformations that underlie chemistry? Well, there's two ways. One is we see and visually observe what is the reaction or what is the chemical or what is the element. We observe them, and those observations, usually we write these down in a lab notebook or we make some sort of documentation or recording of them, but these observations can be qualitative in nature. In this, we think of qualitative descriptions as sort of visual identifiers or as descriptors. So for example, sodium chloride is a white crystalline solid. That would be a qualitative observation of sodium chloride. That is what we observe, and that is what we write or record if we were given a sample of sodium chloride. Or for example, iron is a brown rust-like appearance. So that is a qualitative observation for iron. So like that, you can describe what we see in terms of visual descriptors. You can also describe and record what we see quantitatively, and usually quantitatively, as derived from the word quantity, has some sort of number affixed to that particular observation. So for example, sodium chloride is white crystalline. That is a qualitative observation that I just note. But if I want to go further in my observation, I can state that sodium chloride, 1 mole of that has 58 or so grams. So by introducing a number to that observation, I have made a quantitative description. The density of water is 1 gram per mil at 25 degrees C. So that is a quantitative description in terms of me describing a certain property of water. Another way we can document or understand these transformations is by not just recording what we see, and also what we smell, or if there's any heat, or if there's any type of color change. But a lot of the chemicals or chemistry in general relies upon us to understand properties. So properties are sort of innate to the system. So as an example, a property of me would be that I have black hair. I was just born with that property of having black hair. We subdivide properties as those that are being chemical in nature. So chemical properties are those that underscore any type of reactivity that's intrinsic to them. So as an example, the sugar glucose reacts with the sugar glucose reacts with oxygen to yield carbon dioxide and water. So that is a combustion reaction. I've just described a chemical property of the sugar glucose. Coming back to the example of sodium chloride, a chemical property of sodium chloride would be perhaps that it's completely soluble in water. So I've described a solubility property of sodium chloride, and that's some sort of chemical nature to it. The element sodium, when it burns in a flame, yields a very bright, maybe orange-greenish color. That's a chemical property of the element sodium. In fact, all elements of the periodic table have some sort of chemical property when you put them close to a flame. So chemical property as a type of property deals with reactivity. Then we have physical properties. So this is sort of innate to the material or to the system. Physical properties, again, can be qualitative or they can be quantitative. Melting point and boiling point are very, very classical examples of physical properties. So the boiling point of water, 100 degrees C. Water is colorless and has a very low viscosity. All of those are physical properties. Water was, quote unquote, born with those physical properties. Now remember, I'm not talking about any chemical reactivity, whether water or any other chemical reacts with one other substance or another substance. That would be a chemical property. Here we're dealing with properties that are sort of innate to the chemical material or whatever system you're talking about. Extensive properties are properties that depend on the amount of matter you have, and intensive properties are properties that do not depend on the amount of matter you have. And in our lecture notes that we will go over, we'll give you some examples of extensive and intensive properties.